And today we are going to solve the problem 3.39 of Griffiths third edition Introduction to Quantum Mechanics. The problem 3.39 is very interesting. Find the matrix element of uh, n x n prime. Uh, that is the inner product of x with n and n prime, and also n p n prime in the orthonormal basis of the stationary state for the harmonic oscillator. You already calculated the diagonal element n equal to n prime in the problem 2.12. You don't worry about this. Use the same technique for general case. Construct the corresponding infinite matrices of x and p so that 1 over 2m p squared plus m omega squared over 2 x squared is equal to h is a diagonal one in this spaces, or its diagonal element. What you would expect? Partial answer is the inner product of x with n and n prime is equal to square root of h cross over 2m omega square root of n prime delta n prime minus 1 plus square root of n delta n prime n minus 1. So we know in theoretical lecture we have seen the annihilation operator A cat is equal to 1 over square root 2 square root of m omega over h cross x cat plus I 1 over square root of 2 p cat over square root of m h cross omega, and the air dagger annihilation operator is just this plus you make it minus, so complex conjugate of this one. Then from these two you can evaluate x prime x cat is equal to, if you add these two a plus a dagger or a dagger plus a, the second term will go away because this is positive, this is negative, and you will get 2 times the first term, and after simplification you will get x is equal to square root of h cross over 2 m omega a dagger plus a. Similarly for p, you subtract the a dagger minus a, then the first term will go away, you will get second term. So after simplification you will get p cat is equal to I square root of m h cross m omega over 2 a dagger minus a. So now we got the operator x is equal to square root of h cross over 2m omega a dagger plus a. Now you take the inner product, that is expectation value of x, take the inner product with n and n prime. So which is equal to, you take this one as common, the square root of h cross over 2m omega. This can be separated into two inner product. One is n a dagger n prime, second one is n a n prime. So now what will happen, we have seen in theoretical lecture that when a dagger creation operator act on n prime, this increases the energy state by 1, that is n prime plus 1 with the coefficient square root of n prime plus 1. This we have already seen. Then what about this? When annihilation operator act on n prime, this will reduces the energy state by 1. That is n prime minus 1 with coefficient square root of n prime. We know this will be non-zero only when n and n prime plus 1 is equal, both are equal. That is delta n prime plus 1, both must be equal. We can take this as a square root of n prime plus 1 delta, that is Kronecker delta n n prime plus 1. Similarly here, this will be 1 only when n is equal to n prime minus 1. So this will become square root of n prime delta n prime minus 1. So this is for the expectation value of x. Similarly, you do the same for operator P. By definition, operator P is equal to I is square root of h cross m omega over 2 a dagger minus a. So then the expectation value of P is equal to the inner product of P with the n prime. So which will be equal to, you can take this as common, I square root of h cross m omega by 2, and it can be separated into two parts. N a dagger n prime minus n a n prime. So when a dagger act on n prime, as usual, this will become rises the state by 1. That is n prime plus 1 with the coefficient square root of n prime plus 1. Same is the case with this. It reduces the energy state by 1, n prime minus 1 with the coefficient square root of n prime. Here only the difference between the expectation value of x and p is here you have minus, and also you have I here. So here this is equal to this inner product is non-zero only when n equal to n prime plus 1. So Kronecker delta. So delta n prime plus 1. Same is the case with this. This is non-zero only when n is equal to n prime minus 1. That is square root of n delta n prime minus 1. This is the expectation value of P. Now we will form a matrix because this is the matrix element of X. Here, according to the track notation, this bra is a row vector, row element in the matrix. This is column element, column. Bra vector is row and get vector is column. Now we will spend some time here so that we can understand this. This start from zeroth column. Zeroth column. I have put downward arrow, and first column, second column, third column, fourth column, fifth column, sixth column. Similarly, row. This is zeroth row, first row, second row, third row, fourth row, fifth row, and sixth row. Now you take the first term. First term, if n prime is 0, it will minimum value is 0. Then you will get n is 1. And what will happen? This is first row. First row is this one. This is first row. Remember that this is zeroth row. This is first row, and zeroth column. Zeroth column is this one. So this element is n prime is 0. 0 plus 1 is 1. So this will be square root of 1. Then next you take n prime as 1. If n prime 1 is 1 means n is equal to 2. That is second row. Second row is this one, and first column is this one, is equal to 1 plus square root of 1 plus 1, 2, square root of 2. Then you take next, let it be 2. If it is 2, it must be, n must be 3. That means third row, you have third row, and second column is square root of 3, because n prime is 2, 2 plus 1 is 3, square root of 3. So it will go on. Now you come to second one. Second one, here the n prime minimum value is 1. So you cannot have 0 because it will go to minus 1. So it is 1. 1 means n minus 1 means 1 minus 1 means 0. N is 0 and n minus 1 is 0. So n that is n prime is 1. So that means zeroth row is this, and first column is this one, first column. Square root of n prime, here n prime is 1, so you will get 1. In the same way, you will get this square root of 2. That is, let it be 2. That means it is 1. So, first row is this one, and the second column is this one, square root of 2. So, this will be square root of n prime 2. So, it will go like this. So, this is the way how to form a matrix. So, this is X matrix. Of course, you have to multiply this by square root of H cross over 2 m omega. So in the case of X matrix, we got this half diagonal element. That is both lower half diagonal and upper half diagonal matrix. Then if you square it, you will get the diagonal element are 1, 2, 3, 4, 5, 6, 7. If you square it, this will become H cross over 2m omega. And the second half diagonal element, upper up diagonal element is square root of 1 into 2, square root of 2 into 1, and square root of 3 into 4. It will go on. Similarly, the lower, that is second diagonal. This is a but main diagonal element. This is first half diagonal element and the second half diagonal element. You will get same thing. Square root of 1 into 2, 2, square root of 2 into 3, square root of 3 into 4. Since it's a very straightforward multiplication, that is you are squaring it, I am not doing it here. So I will take the final result here as it is. Similarly, the expectation value of P is, by definition, we have defined like this. I is square root of H cross omega over 2 and square root of n prime plus 1 delta n prime plus 1 minus square root of n prime delta n prime minus 1. It is exactly same as matrix for X except this multiplicative factor, and here you have a negative sign. So it can be written as I square root of H cross omega, m omega over 2. And here you can see this is exactly the matrix, not the multiplication factor. This matrix is same as a X matrix, except here you have negative sign. So lower half diagonal elements are positive and upper half diagonal elements are negative. But for that, no difference except this multiplicative factor and sign of the upper half diagonal element. So we will see what about the p square value. From P matrix, we can find the P squared matrix. If you square the multiplicative factor, I squared will become minus. So this is H cross m omega over 2. And this matrix is similar to the X squared matrix, except these diagonal elements are having negative sign, minus 1, minus 2, minus 3. It will go. So similarly, the upper half diagonal element is minus square root of 1 into 2 minus square root of 2 into 3. It will go like this. In the case of X squared, all are plus positive. You remember that. Now we will move on to the Hamiltonian matrix. Now the Hamiltonian for harmonic oscillator is H is equal to 1 over 2m p squared plus half m omega squared x squared. You replace p squared and x squared matrices. It's a little bit lengthy but straightforward. And add both. Then you will get half H cross omega and diagonal element, non-zero diagonal element. All elements are 0. The main diagonal elements are 1, 3, 5, 7, 9, 11, 13. You remember that the energy, nth state energy for harmonic oscillator is equal to n plus of H cross omega. So naturally, n is 1, you will get half H cross omega. Sorry, n is 1, n is 0, you will get half H cross omega. And n is 1, then 3 by 2. Here you have 3 by 2 H cross omega. So this will be always odd number, that is because this is plus 1 over 2. So if it is 2, you will get pi by 2. So if it is 3, you will get 7 by 3. So exactly matching with the energy level of the harmonic oscillator. So thank you very much for watching my videos and supporting me continuously. Thank you very much.